Hi everyone and welcome back to PrepFusion. I'm Manish and today we will start with the lecture 46 of our induction motors chapter, right? So today we will discuss about speed control of induction motor. Also we will discuss about few theoretical points like what is skin effect, what is like deep bar rotor. We do something in the construction of the motor so that it can perform better, give better performance, better speed control, better torque, better uh, power, right? All those things, lesser slip. Okay, so to do that we have to do few modifications on our induction motor. So these are the modifications like like we do deep bar and we have double cage rotor, right? Also there is effect known as skin effect, so that also we will discuss. So let's first discuss about the speed control. Speed control meaning I want to control the rotor speed. So what is my rotor speed actually equals to? The equation for rotor speed is very simple. It is equals to 1 minus s into the synchronous speed, right? That is what my rotor speed is equals to. So here what are the two things that can vary? So I can either vary my slip or I can vary my synchronous speed, right? So slip, how can I vary? So what does slip depends on? So slip, we will see, we will change the we will try to change the slip with some with either voltage or rotor resistance. We will see how we can change the, how we can control the slip. Basically we will see that. Synchronous speed, how can I control? So synchronous speed is what? 120 f by p. So of course you will not change the number of poles while the machine is running, right? So this you cannot change. So what is changeable? Only frequency. So frequency only we can vary. So we can only vary frequency. Okay, so this is what we will change. Basically we will try to change the frequency, that's it. Okay, so I cannot simply just change the frequency, because if I just change the frequency then what will happen to the flux, right? Flux will change, right? I want to keep the flux constant. To keep the flux constant, if I'm changing the frequency, I have to change the voltage as well. So that is kind of a trade-off. So it's not like I will be able to increase the frequency. I have to reduce the frequency. That's it, right? If I increase the frequency, voltage will be increased, so machine might get damaged, right? So that is one thing that you have to be careful about. So slowly we will discuss about each things. How can I change each things? Okay. So here if I see that, yeah, there are two kinds of, like mainly three kinds of control. One is the stator voltage control, through which we will change the slip. We will see how we are able to change the slip. Okay, how I will show you how we are able to change the slip. Rotor resistance speed control and V by F control. So how adding rotor resistance will change the slip, we will see that, don't worry. Okay, so let's come to the first one, that is stator voltage control. So you want to change the slip. How can you change the slip? So what is slip equals to? Slip is simply ns minus nr divided by ns. So keeping ns constant, so only nr can vary. So basically I want to vary the nr, right? So what we will do, we will change the developed torque, because if you remember, this is the graph, right? This is the characteristics of my torque speed characteristics of my motor, and this is the load torque, which is always constant. So let's say this is my operating point. I am currently operating in this point. Okay, so what if I change the graph? Because what is torque equals to? So if you remember, the value of torque is equals to, torque is equals to 3 upon omega s into v square into r2 dash into divided by the slip. This was divided by the slip. If you remember, slip was coming in the expression. Like this is the actual power gap resistance that I'm seeing, right? Power gap power basically. So air, sorry, not power gap, sorry, air gap power, air gap power. Okay, divided by, like I'm directly writing it in terms of the voltage. Okay, I could have written it I square into R2 dash divided by S. What is I? I is V square divided by the impedance, that is R1 plus R2 dash divided by whole square S plus X1 plus X2 dash. Okay, so that is the thing over here. That is the thing over here. Now I have to, if I somehow increase or reduce the developed torque. So if I somehow change the stator voltage, okay, if I change for this, if I change the stator voltage, what will happen? If let's say I am reducing the stator voltage, if I am reducing the stator voltage, then the torque speed graph will simply shift down. So now it will shift down, right? So if it shifts downwards, what will happen? Because I'm reducing the voltage overall for the same, if everything else is same, if I'm reducing the voltage, then the torque graph will shift down. Basically torque value will be going down, right, for the same amount of speed. So basically if I see what is happening now, this is the stable operating point, right, what both of them intersect. So if I see here, the speed has reduced. Previously the speed was here, now the speed has reduced. So this is how I will control the slip, basically by reducing the developed torque. This was the initial speed, now this is the final speed. Okay, so yeah, I hope you have understood this basic point. So that's how, by controlling the stator voltage, I can control the developed torque. I can control the developed torque. Or what I can do, by changing this, what is my torque? Also my torque is equals to 3 by omega s. I have mainly, my main target is to change the torque. So it is 3 by omega s into I2 dash whole square into R2 dash divided by s. So what I can comment, what I can say is, basically I can add external resistance. If I add the external resistance overall, then also the torque can reduce. So if you remember in rotor resistance control, in the starting methods, if I had added the rotor resistance, the torque was increasing, right? Starting torque was increasing. So something similar will happen if I assume that the current is almost constant. If I am adding external resistance, what I will observe? I will observe that the torque is increasing. So now the torque will increase. Okay, so the speed also will increase. Like stable point will be lying somewhere around here. So speed also will simply increase. So these are the things that you have to keep in mind, basically. Okay, so yeah, basically, right, what is your torque dependent upon? So if I assume, like for the stator voltage, now let's check for the stator voltage. What does my torque depend on stator voltage? Okay, if I want to write on stator what does my torque depend upon, right? In the stator voltage control. Now I am just changing the voltage. What will happen? So what is my torque value equals to? So torque value we have already discussed. Torque is equals to 3 by omega s into v square into R2 divided by s divided by R1 plus R2 whole square plus x1 plus x2 whole square. Okay, so in low slip region, what will happen? In low slip region, now again we will do some approximations, right? I just want to check what does my torque depend upon. Previously also we did that, if you remember, where we are plotting the torque speed characteristics. So in low slip region, what happens? In low slip region, basically this will dominate, right? Because s equal to 0.05, so R2 upon 0.05 will be very high value. So this overall thing will dominate all of this. So basically I can roughly say my torque will be proportional to v square. Here this will become R2 dash by s square, R2 dash whole square by s square, and this will be R2 by s. So ss will cancel. This is also R2 dash. Like I don't care, R2 dash is a constant number because I am varying the voltage. So this will be v square into s, right? So basically what I can say is, like remember one thing, like I have told you, right? Actually what is happening? Actually the developed torque is changing. Due to that, the operating point is changing. At steady state, what must happen? At steady state, this is my developed torque, at steady state my developed torque must be equals to the load torque at steady state. So for a certain second the developed torque value will change and again it will stabilize, right? But at steady state this must satisfy. So basically from here I can say directly that my, if this is constant, that means V square into S is constant, V square into S is constant in steady state. If this is constant, that means my slip is inversely proportional to voltage square, inversely proportional to voltage square. Okay, so that is what is happening to the slip with respect to the voltage. So if I increase my voltage, then the slip will reduce. If I reduce my voltage, then the slip will increase. Okay, so this is how we can control the slip. Okay, now this is what happens in low slip region. So let's do a analysis for the current. Okay, so what is current? I2 dash. I2 dash roughly, right, in low slip region, like this is mainly used for control in low slip region. Okay, we will control this in low slip region. We will not use this slip control method, sorry, stator voltage control in high slip region. For that we have the resistance. Okay, low slip region we will use this. Okay, so what is happening to the current? Roughly the current will be voltage upon the resistance, that is R2 dash divided by S, right? R2 dash divided by S, which is equals to V into S divided by R2 dash. Okay, so what have I told you? I have told you V square into S is constant, that is TD, right? V square into S is constant. So but if I am, let's say it now V square into S is constant, right? So if I multiply and divide by voltage on both sides, this will be V square into S divided by R2 dash into V. So this will be equals to, basically this is constant, like basically my current, right? I can say this is constant, R2 dash is constant. So basically my current I2 dash is inversely proportional to voltage. It is coming out to be inversely proportional because this is constant, V square into S is constant. Okay, due to the load torque, because at stable point both load torque and the developed torque should be same. So although it will not always be the case, but here the current is inversely proportional to voltage. So if I will reduce the voltage, current will increase. So same thing is written over here, that the voltage, if I reduce the voltage by 1 by root 2 times, then the supply current will reduce by root 2 times. If I reduce my voltage by 1 by root 2 times, supply current will increase by root 2 times. So this will cause overheating. Okay, so that is the problem here, that is the problem over here. So that is one of the disadvantages of this method. Okay, so remember again, two things to remember. We will only use this speed control in low slip region. Low slip meaning where the slip is very low. Okay, that is what low slip means. And we will basically another drawback of this method is basically if I reduce the voltage, because I cannot increase the voltage, right? I cannot increase, else the machine will get damaged. So I will only reduce the voltage. If I reduce the voltage, then the current also increases. Okay, that is another disadvantage of this method. Okay, so yeah, so it is simple to implement. So we can use a voltage controller that can reduce the voltage, applicable to fan and blower type loads where the torque demand is lower. If the torque demand is lower, then we can use this, because torque also will change by a lot amount. If I reduce the torque by, like if I reduce the developed torque by a lot, right, then the motor will not start. So this is only applicable for loads which is like, for which low loads, less what do you say, lower loads, right, offers very narrow speed range, because I am only operating in low slip region, right? Low slip region meaning, let's say your S will vary from like S will vary from 0.1 to 0.01. So here, right, the gap is very low. Basically, if you see, if I take example, what is NS, let's say will be 1500 RPM. What will be in R? In 0.1 slip, it will be 0.9 into 1500. So it will be 9 into 150, 9 into 150 is 450, so 1350 rpm. Okay, in the first case. In the second case, what will be ns? Second case, this will be in 0.99 into 1500 rpm. So this will be basically 1 4 15 if I subtract, right, 15 if I subtract 185 rpm. So if you see, the speed control range is only almost around 150 rpm. Okay, I'm only able to control 150 rpm of speed. So that is the disadvantage. We'll see in the like resistance, external resistance control, it will be better. So there will be high losses and poor efficiency at lower voltage. Why? Because the currents will increase. If the current increases, there will be copper losses, right? I square R loss in the rotor windings, resistance, and the stator winding will increase by a lot. So it is not that suitable for low voltage operation. Okay, so now let's check for the rotor resistance speed control. What will happen in the rotor resistance? So this can only be used in slip ring induction motor. Okay, this, because I can connect the rotor resistance only in the slip ring induction type motor, right? So can only be slip ring induction motor. Okay, so what we do, basically I told you, right, if I keep on adding my external resistance, the rotor graph will just shift on the left hand side, correct? We can do it. So basically this is my initial graph. This we have discussed in the previous lecture, that this is my torque, developed torque, and this is my load torque. Okay, so this is my like developed torque, basically TD. So if I keep on adding the resistance, the graph will just shift backwards. This we have discussed in the previous lecture only. The graph will just shift backwards, right? Maximum torque will remain same, maximum torque won't change, but the graph will just shift backwards. Okay, so basically what happens, that your R external one is will be less than R external 2 will be less than R external 3. Okay, so yeah, so that is the thing over here. So if I keep on increasing my rotor resistance, then the graph will shift backwards. So balance point, stability point also will shift, right? Initially this was a stable point, now this is a stable point, now this is a stable point. So speed will reduce, speed will basically reduce. Okay, so how else can you understand this? So I'm just thinking, if I keep on so what we can do, this is generally done in the near the high slip region. So we generally control the speed near the high slip region. This is the point 1 for slip ring induction motor. Point 2 is high slip region. So in the previous case also, during the starting, what was the slip? Slip was very high, right? In the previous lecture, the slip was very high. That's why I did not mention there that approximation that we are doing. So what kind of approximation? So what is my I2? So my I2 is equals to V upon under root R1 plus R2 divided by S. So roughly I can say, as it is high slip region, R2 divided by S is roughly equals to R2 only. Okay, that is my approximation that I am doing. So this will be R2 whole square plus X1 plus X2 whole square. So roughly I'm not changing the current. So current is constant. Okay. So again, what is the torque? Torque, developed torque is 3 upon omega S into I2 into R2 divided by S. Okay, and again I have told you that R2 divided by S is roughly equals to R2 only. So I can directly say that this will be equals to, like, this will be proportional to R2. Okay, because I2 is constant, S is S. I will discuss about S later on. So roughly is proportional to R2. Sorry, I can say, okay, this will be proportional to R2 divided by S, because I2 is constant, right? So, and I know that the load torque has to be constant, right? Load torque has to be constant. So at steady state, the developed torque will be equals to the load torque. So basically from this equation I can get R2 by S is constant. Constant. So if I increase the R2, then the slip also will increase. So basically I can say from this equation, so in the previous lecture I did not mention it because there we were not discussing about the speed control. So here my R2 is proportional to slip. So basically this is a underlying equation that if I increase my slip, the rotor resistance, like if I increase my rotor resistance, the slip will increase. What does slip increase means? Slip increase means rotor speed will reduce. So that's why you are seeing rotor speed is reducing. That's why the graph is shifting backwards. So the steady state point is shifting backwards. But all this, remember, is with one approximation that it is in the high slip region. Okay, we are doing this approximation. Remember, this is a very, very important approximation, right? Don't ignore this. All this we are doing in high slip region. So if I keep on increasing my R2, basically R2 is what? R external plus whatever is the winding resistance. Okay, so if I keep on increasing my R2, the slip will increase. So that's it basically. So that is this method, right? So yeah, that's how we control the speed using these two methods, rotor resistance and the this stator voltage control. Okay, so yeah, this method is applicable only in slip ring induction motor. It will not be applicable in squirrel cage because there is no provision for adding external resistance. Also remember, this method is applicable only at high slip region, because there we assume that to be almost constant. Basically, actually one more thing I can say, okay, even though okay, but no, that approximation, no, yeah, high slip region only, then only we can do this approximation, right? High slip region, basically S is very near to 1. Okay, otherwise we will not be able to do that approximation. So as resistance increases, the slip at which maximum torque shifts towards S equal to 1. S equal to 1 is here, right? This is NR equal to 0. If NR is 0, S is 1. So we shift on the backwards. Okay. So yeah, hence the motor speed decreases. Key insights, allows smooth control of speed in low speed ranges. Okay, so in low speed ranges it will allow smooth control, because low speed means what? High slip, because slip and speed are just inverse, right? If you see here, it is speed is reducing, slip is highest. Here slip is lowest, speed is the highest. Okay, so that's why it is called as allows smooth control in low speed region or high slip region. Okay, however, slip power is wasted in the heat as resistors are there, right? So of course whatever currents will flow, so there will be heat loss in the external resistors, that will be present, we cannot avoid it. So efficiency will go lower. It is useful in high starting torque application. So basically wherever high starting torque is required, I can shift the slip maximum torque to the left hand side so that I get the maximum torque during starting. Okay, so that's why it is used in cranes and elevators, all those things. So there is a bit of improved scheme that we use because we don't want this power to get wasted. So what we will do is we will use, rather than wasting the slip power as heat, it is converted and fed back to the supply using power electronics. So basically what we'll do, we'll connect a load that is not a resistor, that is a power electronic load that will be able to change the current and voltage, right? So we will not waste, dissipate the energy, we will return whatever power that power electronics device is taking, it will fed back to the supply. Okay, not important, this is just a theoretical concept that I am explaining. Okay, this will further enhance the efficiency. Okay, this can be asked as a theoretical point, that's why I am telling you. So this can be further basically used to enhance the efficiency of the speed control scheme. Okay, so this is one modification that we can do to improve the efficiency, because energy is getting lost in the external resistance as the form of heat. Now we will go to the third kind of speed control, that is V by F speed control. So again we know that the synchronous speed is what, ns is 120 f by pi by p. So if I am able to control the ns, right, because basically if I am able to control the ns, then the rotor speed will be controlled, because nr is 1 minus s into ns, right? So of course I cannot directly I cannot directly reduce the flux. If I reduce the flux, right, okay, sorry, I cannot increase the frequency. If I increase the frequency, then the voltage has to be increased, and that I don't want. I don't want to increase the voltage because that will damage the whole system, right? I can only reduce the voltage, I cannot increase the voltage. Okay, so but there are few problems. What kind of problems are there? So one thing, okay, no, what kind of, so my flux, right, flux will be constant, flux is V by F. So if I am reducing the voltage, the sorry, if I am reducing the frequency, the voltage also will be constant. So flux, as it has mentioned, it will have a constant flux operation, because if I just reduce the flux, there can be saturation, right? There can be saturation in the core, then the machine will not operate properly. Okay, so that is one thing. Now let's discuss about the maximum torque. What will happen to the maximum torque? So if you remember, we had derived, no need to remember this, but we had derived this expression for the maximum torque. What was the expression? It was 3 by omega s into v square divided by 2x 2 dash. This was the expression for maximum torque. Now what are the frequency dependent terms over here? So if we see, omega s depends on frequency directly. What is omega s? In the previous lecture also we had written it. It is 4 pi f by p. That is what my omega s is equals to. What is x2? x2 is directly proportional, right? x2 is directly proportional to the frequency. x2 is directly proportional to the frequency. Okay, so from here what can I write? It is proportional to the frequency. Yeah, it is proportional to the frequency only, because yeah, so I can write that my torque, right, torque is proportional to v square divided by, this is proportional to f, this is proportional to f, so this will be v square divided by f square. So torque is proportional to v square divided by x square. Now this has to be constant, right, and the maximum torque also has to be constant. If I want to keep the maximum torque constant, what I have to do? I have to simply keep v by f constant. So this is also another reason for to keep the v by f constant. Okay, this is also another reason to keep the v by f constant. So what will happen to the graph basically? So here, right, again in the previous case we had only either we were controlling at high speed region or low speed region, but with this we can control both. How can I control both? So if I want to increase, like let's say this is my rated, f equals to f rated. If I want to go beyond my rated speed, what will happen? I cannot increase my voltage, machine will get damaged. So I will increase my flux. If I increase my flux, what will happen? That I am increasing the flux, right? Voltage I am keeping constant, so the maximum torque will go down. So basically there will be two regions. So with VYF control, directly I can control two regions. One will be above base speed and below base speed. Base speed meaning at rated voltage, rated frequency. So this is speed, this is torque, and this is the ideal speed torque characteristics. Okay, let's say this is the slip at which the maximum speed occurs, right? So speed at which the maximum slip occurs. So this is my maximum torque. So what we'll do, this region, this is the base speed, this point is the base speed, right? If I'm going above the base speed, this will be called as the above base speed, and this will, the left hand side will be called as the below base speed. So actually, right, what I have to do, I have to TK, I have to make it bigger actually, that will be easier. Okay, and this, right, if I get even backwards, this will be called as the below base speed. Okay, so now what I can say is, if I am above base speed, that means I cannot here, right, here voltage will be constant, I cannot increase the voltage, that will damage, but frequency will increase, right? So if frequency is increasing, what is happening to the maximum torque? Maximum torque is reducing. So this is my standard speed torque characteristics. Okay, this is the maximum torque, and my what can you say, what is happening if I'm going above base speed, what will happen? Frequency will increase, but the voltage will be constant, hence the maximum torque will reduce. So overall the torque will reduce only. So overall the torque will reduce. Okay, so if I plot the graphs for above speed, overall the maximum torque will reduce. Okay, so if I am increasing the speed, overall torque will reduce. Basically the motor may go out of stability, that also can be possibility, because let's say my load torque is this. For the motor to work in stable region, what needs to happen? What needs to happen? Mark it with white. Load torque must be equals to developed torque. So let's say if I keep on increasing the speed, and there comes a point where the load torque even goes below the maximum torque. So there is no intersection. So there is no point of like stability. So this is basically the motor will become unstable. So you cannot just simply keep on increasing the frequency. I mean, keep on increasing the speed. If you want to increase, you cannot just simply increase the NS indefinitely. So motor will go out of stability. It will not rotate. Here the motor will be just lock. Lock meaning NR will become 0, because it has not developed enough torque to move the mechanical load. Okay, so that is the thing over here. Now below base speed there is no problems. because below base speed, what do? Below base speed, the V by F is constant. If V by F is constant in this region, the V by F is constant. If V by F is constant, that basically means that here the torque speed graph, the maximum torque speed graph will be almost same, just it will be bring back. Okay, so what will happen? Starting torque will also will increase. If I have any other colors, possible other colors, yeah, this is one of colors. So basically torque will only increase, it will not reduce, torque will only increase. Okay, so that's a good thing. Okay, so that is the case over here. So here in this region the V by F will be constant, hence the maximum torque will not change, but here maximum torque will reduce. Okay, that is the only thing that you need to understand. Okay, so if I am going above base speed, I cannot just indefinitely increase my speed. There has to come a point where this will be a problem, right? Instability. Okay, so that is what is written over here. Below base speed, both voltage and frequency are reduced as flux remains constant, hence the torque also will be constant. Motor speed decreases smoothly. Above base speed, voltage is kept at rated value to avoid insulation breakdown. I cannot go beyond the rated value. Frequency is increased beyond the base speed, so V by F decreases, flux reduces, torque reduces. So basically here the power will be constant. How the power will be constant? So this is the point where my torque is constant. So below base speed, it is constant torque region, because torque is constant, because torque is proportional to the flux, right? Above base speed, it is constant power region. How come? So we know what is torque, we know what is power. Power is omega s into torque. So what is torque proportional to? Torque is currently proportional to V square by F square, right? If I am not mistaken. So V is to okay, V by F flux basically. So okay, just hold on, give me 1 second. Slip torque. So this is the maximum torque relation. If I want to write this, okay, omega s. Okay, this is the air gap power. What is the air gap power? Air gap power is 3 into I2 square into R2 dash by S, correct? So this is my air gap power. So here what is my I2 dash equals to? So if I'm changing the, so okay, here I'm not changing anything, right? I'm not changing literally anything except the slip. Slip can change. So this will be 3 V square divided by R2 dash divided by S whole square plus R1 whole square plus x1 plus x2 dash whole square into, this is whole under root, right? Whole under root into R2 dash divided by S. Now if I assume that we are like, if I assume that this quantity is very big than the other quantities, so basically what will happen? R2 dash divided by S, R2 dash divided by S will be cancelled. So basically my power will be only proportional to voltage square, right? So as I'm not changing the voltage, voltage is constant, so power also will be constant. So voltage is constant, so power also is constant. Voltage is constant, power is also constant. Okay, so that's why it below the base speed it is known as the constant constant power region. Okay, constant power drive. So above base speed is known as the constant power region, below base speed is known as the constant torque region. Okay, so you can see the like efficiency is very good because we are not adding any resistors and stuff. Why we are getting a wide range of speed control. In the previous one, either we were able to control high in the high sleep region, or we were able to control in the low sleep region. Both the regions we are not able to control, but with this we will be able to control both the regions. But this basically integrates external circuitry. Okay, so limitation, so here, right, another, so this is the same thing only, so I can copy this limitation here. okay, this limitation won't be copied here. So basically one is cannot increase the voltage above the rated value. Of course, in the high speed region we cannot do it because I cannot increase the voltage to keep the flux constant. That is a disadvantage because there will be insulation failure. One more thing is we need the external circuitry, right? So actually this is not the advantage, this is not the advantage here, right? We will need the external circuitry which is costly, so I have to include this in the disadvantage. Because all this, like, someone has to change the frequency, and changing the frequency is not that easy of a task. So all this will increase the cost and like external circuitry is required, right? So the maintenance also will be increased. So these are the disadvantage of this kind of basically speed control techniques. So mainly these are the speed control techniques. So here stator voltage control, we control range is narrow. So basically it is a what? It is operated in the low slip region. Low slip region. Motor type, all types of motor can operate, but efficiency will be lower again because because my volt current, right, I2 is proportional to inverse of voltage. So the more the voltage reduces, that current will increase very sharply. So that's why the losses will be there. That's why efficiency is low. Okay, generally used in fans and blowers. Rotor resistance control range is higher because here we are operating in high slip region from 0.9 to 1. So we will get a wider range here. Okay, previously we did not get a wider range, but we will get a wider range. But the problem with this is, again, it is only possible in slip ring induction motor. It is not possible in any other induction motor. Okay, so efficiency again will be lower. We can improve the efficiency with slip power recovery. Why it will be lower? Because there will be losses in the external resistance. Okay, so these are my applications, basically hoist cranes. Okay, then of course we like the modified version of this is the slip power recovery. I'm not discussing about that. Then we can use the VYF control. We will get a very wide range of speed control. All types of motor can be used, and efficiency will be higher because here we're not adding any external resistance or current is not increasing very highly because the flux is constant. Okay, so this is actually used in most cases, mostly used. Okay, this is the most important one that mostly the modern industrial drives use. Okay, to use the motor. So yeah. So let's, okay, one thing I forgot to do. So let me draw the graph. Basically let me draw the graph. I forgot to draw the graph. Like, this is similar to DC motors, right? If you remember, in DC motors we had drawn a graph like this. Okay, I will draw the graph here only. Okay, so this is my omega, and above base speed, what is happening? So either it is torque or power. So torque, let me do it with yellow, and power, let me do it with orange. Okay, so torque, right, below base speed will be constant because the flux is constant. So torque will be constant below base speed, but then as the flux as the above base speed, so this is base speed, basically omega rated. Okay, base speed. Above base speed, what is happening? The frequency is increasing, but the voltage is constant. So V by F is reducing. So flux is reducing. If flux reduces, the torque will reduce. Flux reduces, the torque will reduce. So torque will just simply reduce. This is the graph for the torque. What about for the power? So above base speed, the power is constant. So it will be constant because what is power? Power is 3 into I2 square into R2 dash. Okay, R2 dash divided by S. So it is basically proportional to voltage. So voltage is constant, so the power also will be constant. Okay, below base speed, what is happening? Below base speed, so what is the torque equals to? So I know my power, right, is basically what? Omega into T. That is what my developed power is, omega into T, torque. So from here, if I want to mention that torque will be constant, and if I am, like, I'm going backwards, if I'm reducing my frequency, that means my omega is reducing, because omega is proportional to frequency itself, right? So if I'm reducing omega, so if I'm reducing frequency, omega will reduce. So if omega is reducing, power will reduce, because this is constant, torque is constant. So basically it will just follow a linear relationship. Okay. So yeah, it will not be exactly here, it will not be exactly linear. Of course, there will be differences, it will be like non-linear, but just drawing a rough diagram. Okay. So above base speed, it will just operate as a constant power drive. Below base speed, it will just operate as a constant torque drive. Okay. So these are the two equations. I hope you have understood this point. Okay. So one more thing is, how can I find out the torque equations below and above base speed? Okay. So below base speed, the torque is constant. So if below base speed the torque is constant, that means my V by F is constant, right? Below base speed the torque is constant. So I will do the analysis below base speed. Below base speed. So the torque is constant. So if the torque is constant, then what will happen? Then I know what is constant. V by F is constant, right? V by F is constant. So what is the torque in below base speed? So let's take a case that I am very near to this region, in the low slip region. Okay, this is the low slip region, right, where my omega s and omega r are almost equal. Okay, so in the low slip region, what happens? So torque expression, torque torque in low slip region will be what? Torque in low slip region will be 3 upon omega s into what? Voltage square. Like we had already derived this, right? It was almost equals to, if you remember, 3 upon omega s divided by this. It is low slip, right? So basically R2 dash by S will dominate into R2 dash by S. Sorry, this will be R2 dash divided by S whole square, right? Yeah. So basically this will be 3 divided by omega S into V square S divided by R2 dash. This we had already like derived in the previous speed control method, stator voltage control. Now what I want to come to your attention is that here omega is also is dependent to frequency, right? So I can directly write, if my load torque is constant, if my load torque is constant, what I can say? I can say that my torque is proportional to V square S divided by frequency, because 2 pi, all those things are constant. So this is the value. I can say V by F is constant. If V by F is constant, so my torque I can directly say is proportional to voltage into slip. Torque is because V by F is constant, I can take out the V by F. Torque is proportional to voltage into slip, or other way around also I can do. I can multiply frequency on both sides. If I multiply frequency on both sides, this will be F into F. If I multiply on frequency both sides, this will be V square divided by F square into S. Okay, so I can say that my torque is proportional to SF. Now this is a very important relationship. This is only valid, remember, only valid, there is a caveat always, only valid in low slip region. Okay, only valid in low slip region. So what I can say, torque is constant. If torque is constant, then my SF is constant. What does SF means basically? So basically my SF is constant. So I can use this equation, right? So let's say in the case 1 where my frequency was F1, So my synchronous speed also will be ns1, that is 120 f1 divided by p. Okay, so what will be the slip in this case? Slip will be ns1 minus nr1 divided by ns1, right? So from here, this is the slip s1. So I know s1 into f1 will be constant. So in the second case, let's say I'm operating at a different frequency, ns2. Now whatever analysis we are doing, please remember this is only valid in low slip region. Otherwise this will not be valid. Okay, I'm mentioning this over and over again. So ns2 will be equals to 120 f2 divided by p. So this will be s2 will be equals to n s2 minus n r2 divided by ns2. So basically s2 into f2 will be constant s1 into f1. This has to be constant because load torque is constant, because torque is proportional to s into f. So I can equate this, so I can get an equation, and from there I can find out the value of what, of nr2, right? So it will be basically ns1 minus nr1 divided by ns1 into f1, whatever is the f1, this will be equals to ns2 minus nr2 divided by ns2 into f2. So basically I know f1 f2 will be given to me, ns1 I can find out, ns2 also I can find out, nr1 will be given to me, I have to find out the nr2. So from this equation I can find out the nr2. Okay, so that is how you solve basically. So one more thing I can directly write one more thing, that what is my ns1 is 120 f1 by pi. So f1 will get cancelled, 120 by p, 120 by p also will get cancelled. Here also it will be f2 will get cancelled, pp will get cancelled basically. So ultimately the equation, simplified equation that comes out is ns1 minus nr1 will be equals to ns2 minus nr2. Okay, this is a very beautiful expression that will come out, but only valid in the low slip region. Okay, so if the load torque TL is constant, right? If torque is constant, then only S into F will be constant. Then we can apply this. Or a easier way to understand this is, what is S into F? Can I write what is S into F? No, actually there is an NS, right? We cannot actually write. Okay, so yeah, let's ignore that. So yeah, here ns into n. Okay, let's ignore that. Basically, right, what is s1 into ns1? S1 into ns1 is ns1 minus nr1. ns1 is proportional to f. So basically s into ns will be constant. So what they are telling, indirectly they are telling that s into ns, right, s into ns is constant. Okay, same thing, both are saying the same thing. So this is one beautiful expression that you will get in low slip region. Okay, this will only be valid below the base speed, because torque is constant below the base speed. Okay, low slip region, below base speed. So these are the two conditions. Okay, so yeah, I hope you have understood. Let's now solve few questions on this so that we can understand this even better. So I will show you the questions. This is one of the questions, this is the other question, second, third question. Okay, so these three questions you try it out by yourself, and I will try to solve this now. Okay, you try it out, I will try to solve this. So let's solve this 23rd question. Okay, so we have a wound rotor. If I have a wound rotor induction motor operates at, so wound rotor meaning it is a slip ring, sometimes it is also called as slip ring. Okay, operating at a slip of 0.03. So it is operating at low slip region. Okay, low slip region, while delivering full load torque. Okay, so slip S full load is 0.03. I'm delivering full load torque TFL. The rotor resistance per phase R2 dash is 0.25 and an external resistance is connected. R external is connected, that is 0.5 ohms. Determine the new slip required to produce the same full load torque. What will be the new slip required to produce the same full load torque. Okay, so okay, in low slip region, what is my torque proportional to? In low slip region, I know my torque is proportional to V square into S. Okay, remember here rotor is also changing, rotor resistance is also changing, so I have to write down the expression. So what is the full expression of torque? 3 by omega S into V square divided by this whole resistance. In low slip region, the denominator is dominated by the R2 divided by S term, so this will be R2 divided by S into, remember this will be actually this will be squared into R2 divided by S. So this will be equals to 3 by omega S into S divided by R2 dash. Okay, so this is what my torque is equals to, and I'm changing my R2. So what they're telling me is load torque is same full load torque. So what is changing? Omega S will not change because I'm not changing frequency. R2 dash is changing, voltage is also constant, so slip also has to change. Basically slip also has to change, right? So basically if I take the ratio T upon T dash, so all this will remain constant, only it will be S upon R2 dash, right? So it will be S upon R2, let me not write R2 dash, you will be confused otherwise. R2 divide by S dash upon R2 plus R external. Okay, so load torque is constant, so basically S dash will be equals to S, the slip is 0.03 into R2 dash plus R external. R2 is basically 0.25 plus 0.5 divided by 0.25. Okay, so this will be 3, so this will be 0.09. so the new slip required will be higher, 0.09. This will be the answer. Okay, these kind of things also can be asked. You should know how to manipulate the torque equation, what happens with the torque equation. So let's move to the next question. So in this question they are telling me that the induction motor operates in no load condition. In no load means the slip is almost equals to 1, that is in the high slip region. Also no load means the load torque is 0, there is no torque. So developed torque also will be almost there will be some developed torque due to the friction and windage loss, but that will be almost negligible, that will be also 0. Okay, developed torque also will be almost 0. So now they are telling me I am halving the applied voltage of the rated value, then what will happen? Will the speed increase, decrease? Will the current increase, decrease? What will happen? So first thing you have to keep in mind, I am operating in high speed region and the load torque is 0. If the load torque, that is it is operating in no load, then the stability, right, stable point, this is my torque speed graph and I am lying somewhere around here. Okay, the graph is not that great. I am lying somewhere around here, okay, in this region. So here my torque is simply 0, right, load torque is 0. So I am lying in this region, right, in this position. Okay, so my current operating point is this point. So the thing is, what is my torque dependent in high slip region? My torque is basically equals to what? It is 3, like air gap power, like 3 by omega S into the air, like basically the air gap power, which is what, I2 square into R2 divided by S. S is almost equals to 1, right, because it is high slip region, because there is no lag. So S will be roughly equals to 1. So roughly I can say this will be 3 by omega S into I2 square. What is I2 proportional to? So I2, if I write what is I2 equals to, so I2 will be equals to the voltage V upon R1 plus R2 whole square plus x1 plus x2 whole square. That is what my I2 is equals to whole under root. Okay. So from here what I can say is I am having the voltage. All these are constant because R2 by S and R2 is almost equal because slip is 1. So if I am having the voltage, if the voltage is getting reduced to V by 2, then the current also will be halved. Current will reduce, that is for certain. Current will reduce. So speed decreases and stator current increases. No, this is not a possible answer. Both speed and stator current decrease. This can be a possible answer. Speed and stator current remain nearly unchanged. No, current will reduce. But here it is telling speed remains constant, stator current reduces. This also can be a possible answer. Now your first instinct will be that you will directly write here that your torque is equals to I2 is this value, right? Your torque will be roughly V square divided by whatever is the impedance, right? Impedance that is constant, that is some constant value, into R2. So all these are constant. You will say voltage is halving, so torque also will be 1/4. But please be careful in which region I am at. I am here. So torque is almost equal to 0. Torque is almost equal to 0. So whatever torque there is, that is only due to the friction and windage, right? That is the torque that it is supplying due to the air gap, due to the due to the air drag. So torque is almost equal to 0. So if I am doing 0 by 4, does not matter because torque is already very low. Let me take an example. Let's say my torque is currently 0.01 Newton meter. So if you say that torque is proportional to voltage, kind of you are correct. The torque will go to 0.0. If I divide by 4 to 5, but this and this, right, both are very low values. So torque does not change much. So there is very negligible change in torque. That means there is very negligible change in speed because it is already operating in no load. In no load, the speed is almost equals to the synchronous speed. There is no change, right? So speed will not vary much. Speed will be constant. Okay, speed will not vary much. Stator current will reduce. I know you will have confused that speed also will reduce. No, I am operating in no load, so speed is almost equals to the synchronous speed, and here, right, the developed torque is very low. So even though torque reduction is there, but it will not reduce by much. Okay, so yeah, I know this is a confusion because this is a very good question. This is a gate question, gate by IIT Bombay, okay, from 2005. There is a confusion here, right? That's why this question becomes very good. So option D will be the correct answer for this question. Okay, let's now move on to the next one. A three-phase induction motor operates with a full load slip of 3%. A three-phase induction motor operates with a full load slip of 3%. So full load slip is 3%. Okay, that is 0.03, and operating at rated voltage V equals to V rated. What would be the slip value if the motor is required to produce the same torque theoretically while operating in 110%? Okay, slip is very low. If you see, this is in the low slip region, right? In low slip region, I will not derive it over and over again. If you remember what happens in low slip region, basically my torque is proportional to V square S. Okay, torque is proportional to the V square S. What are they telling me? That what will be the slip value if the motor is required to produce the same torque theoretically while operating at 110% of the rated voltage. So basically I can say T1 upon T2 will be equals to V whole square into S1 divided by V2 whole square into S2, because my slip will be almost S this value, right? V square, V1 square S. This we have derived in this lecture, in previous lecture also. So I'm not deriving it again. So because they are telling me that the torque will be same. So basically I can write the slip in the second case will be V2 divided by V1, right? Sorry, slip in the second case will be V1 divided by V2 whole square into the slip in the first case. So basically I can write V1 is V only and V2 is I have increased the voltage to 110%. So this will be 1.1 V into whole square into S1. So S1 is 0.001 0.03. So this will be basically, I can say, like the slip, new slip, right? I can calculate the new slip. What are they telling me? What would be the slip value if the motor is required to produce same torque? Yeah. So the new slip will be 1.1 whole square into 0.03. So 0.024. Okay. So the new slip becomes 0.024. Zero point 0.0248. So roughly S2 will be 2.4, almost roughly 2.5%. So slip will change to 2.5%. Okay. Yeah. So yeah, that is the case here. So slip will be 2.5%. This will be the answer for this question. So let's now understand about a small thing known as skin effect. What is skin effect? So one thing, if we know that if some current is passing through the conductors, right? This is a conductor, solid conductor. If a current is passing through the solid conductor, the current will be uniformly distributed. That is what we know, right? Current will be uniformly distributed. Then the current density will be constant, because we want this only. We want the current density to be constant, because if there is higher current density in one region and there is lower, so this place can get damaged. That's why we want uniform current density throughout. Now all this is theoretical and all this is true in DC. In DC, current density will be constant, but in AC something will happen. In AC, what will happen? In AC, there will be flux generation. In AC, there will be flux generation. Why? Because if I have an alternating current, right? Like DC current also will produce some flux, that is true, but that flux will be constant. Correct? With the direction and the hand, I can say it will also produce a flux, DC current, but that flux will be constant. But in AC, what will happen? The flux will keep on changing. And if the flux keeps on changing, there is a reactance that will come into action. Okay, and that reactance will change the impedance. If the impedance changes, then in some regions the current will be higher, in some regions the current will be lower. Okay, so in case of skin effect, what happens is, as there is huge amount of current change, right? Current is changing very fast, so which will generate a flux, right? And most of the flux, right, leakage flux, will be outside near the periphery of the conductor. Like there will be very less amount of flux in the center of the conductor, right? Most of the flux will be near the periphery. So if most of the flux is near the periphery, that means what? That basically means I will need more current on the outside, because flux is there. Flux is proportional to the current. So basically more of the current will flow through the periphery, because more flux is outside. So flux is proportional to current. So more current will be on the outside, right? More current will be on the outer side than on the inner side. So effectively more current is flowing on the outer side. So this effect is known as the skin effect. That is when most of the current flows through the skin, right? Although the conductor is solid, but it is of no use, because most of the current is flowing outside. It is not flowing inside the conductor. This we will study in power systems as well, more extensively. Okay, here I am just giving you an overview. So what happens in a skin effect, that most of the current flows on the surface of the conductor. Most of the current flows on the surface of the conductor. Okay, so what I can say is, this is a problem, right? Current density increases. So effectively what happens? Effectively the usable area of the conductor reduces. If the usable area of the conductor reduces, what is my resistance? Resistance is rho L upon A. So if A reduces, right, resistance will increase. Okay, so resistance will increase basically. So if resistance increases, is it good or bad? So kind of it is good during starting, in case of a induction motor, I want higher resistance, then I will get higher starting torque. But always it is not desirable. We don't want this always, right? Because at full load, if the resistance is higher, there will be more copper loss, right? More copper loss. I don't want this. So this was about the skin effect basically. So basically the ultimate thing is my AC resistance, right? AC resistance will be greater than the DC resistance. Okay. Why? Because most of the current will flow through the outer periphery, so the effective area is getting reduced. If the effective area is getting reduced, the resistance will go higher. So if the same conductor I would have used for DC, the resistance would have been RDC. If the same conductor I am using for AC, the resistance will increase. Okay, that is the thing that we want to know. So basically at low frequency, case 1, in low frequency the effect will be very low. Basically in low frequency what will happen, in low frequency like generally what happens, due to AC there will be a reactance, that there will be higher reactance in the center. This reactance will be high in the center, and in the periphery this reactance will be very low. So most of the current will flow through the periphery only. Okay, so basically we will have a resistance and a reactance. So in low frequency what happens, low frequency when my F is about 0, near about 0, basically our XL is what? XL is 2 pi FL. So frequency will be very low, so this will be roughly 0. So basically my impedance will be roughly R DC only. Okay, so what we can say, I can neglect in low frequency, I can neglect the skin effect. But when frequency becomes higher, even at 50 Hertz also, skin effect is observable. So in medium to high frequency, medium to high frequency, okay, the what will happen in medium to high frequency, basically the reactance will be considerable in the center, so most of the current will flow through the outside, so resistance will increase. If the resistance increase, of course the outer side current will be higher than the inner side. So here, right, the current is same, basically inner side current and outer side current is same because it is uniform, inside and outside current is same. But in medium to high frequency, the outer current will be higher than the inner current, current density will change in the outer side, so skin effect is observable. Okay, skin effect is observable. Why is the outer current higher than the inner current? Because the reactance, inner reactance will be, sorry, outer reactance will be much lower than the inner reactance. Inner reactance will be higher, that's why the most of the current will flow through the outside. Okay, so here skin effect cannot neglect the skin effect. Now for induction machines, what is important? What is important? The important portion is that because all of this, right, where does the current flow? In the rotor, right? In the rotor the current flows basically, which has magnetic field. So for us it's important that when is the frequency at full, when is the frequency high, then only we can take into effect of the skin effect. So for induction machine, the rotor frequency is what? Induction machine rotor frequency. So rotor frequency is equals to S into F, right? At starting, the slip is 1. So at starting the rotor frequency Fr is F high. Okay, at full load the slip, right, at full load SFL is like very near about 0 only, full load, or like sometimes 0.05 or something, right, very low. low. So the rotor frequency Fr is also low. So we don't have to consider the skin effect in full load. Only the skin effect will come into action in starting, where the rotor frequency will be higher. So that is the key takeaway here. What is the skin effect? Most of the current will flow outside the conductor. The AC resistance will be higher than the DC resistance, and basically for induction motor, like skin effect is observable in high frequency. We can neglect it in low frequency. Okay, and for induction machine, the rotor frequency is S into F, and we know that during starting the rotor frequency is F, so it will be observable during starting, it will be not observable during full load. Okay, so that is the thing over here. So I hope you have understood this points. So yeah, so like we can draw our equivalent conductor in two ways, like two parallel paths. Both of them will have same DC resistance, but their AC resistance will change. So it will have XIN and XO depending on the frequency. Okay, so XO, if F is very high, this will be lower, and XIN will be higher. Okay, so most of the current will flow through here, through the outer side, not through the inner side. Okay, that is what they have written here. Most of the flux will go outside. So they have discussed with flux. I have not discussed with flux. I have just explained you intuitively how it can happen. You can give a read to this, but it's not that important. Theoretical points are written, you can ignore it. Okay, so skin effect, basically most of the current will concentrate near the surface of the conductor, hence the effective area will be reduced, hence the current will flow through the outside. Okay, so like in case of slip ring induction motor, we have already learned that how can I control the like starting current with the help of rotor resistance, right? We have the provision to add external resistance. Okay, that's why we limit the starting current. Also it will improve the starting torque. This we have discussed, right? More air gap power, so more starting torque. Okay, so what we do, initially we increase the rotor resistance during starting, and slowly gradually we cut out of the resistance, so that there is not losses, because if I connect the external resistance there will be copper losses, but continuously I don't want this, right? Initially I want that to get a higher starting torque, then I will cut out the external resistance to basically reduce the losses. There will not be any losses. This provision is already there, right? So for this provision we don't need to use the skin effect. So here, right, we don't need skin effect, no need of skin effect. But in case of a squirrel cage induction machine, if you remember the construction, we did not have any provision to add any external resistance. So here, right, we had no external resistance that can be introduced. So what we'll do, we will use the skin effect to increase the initial resistance. So we will use the skin effect to increase initial rotor resistance, so that there will be higher starting torque, and the this starting current also can be reduced, right? I starting current also can be reduced, and the starting torque also can be increased, right? But do remember that like what is our slip frequency, rotor frequency at starting? It is F2 is equals to S into F, that is F. Okay, so which is basically 50 hertz, almost 50 hertz. Which is 50 hertz. Okay, so in this frequency actually skin effect by itself is not that dominating. So okay, skin effect is not that strong enough to make a difference, right? It will not increase the R external too much. So we have to modify our rotor. Okay, skin effect is there at 50 hertz, but it is more dominant at more like kilohertz, right? Kilohertz skin effect is more dominant, but our frequency is only maximum 50 hertz. So we have to make modifications. So we will make few modifications. So there are two kinds of modifications. One is the deep bar rotors, and another one is the double cage. So in both cases, just remember this thing, whatever we are doing, we are making the skin effect more dominant. That's it. That is the purpose. Why? Because I want to increase my rotor resistance at starting, right? And as soon as, like what will happen, as soon as the motor will accelerate, what will happen? It will reach towards the full load speed, and at full load, what do I know? I know that the slip frequency is almost zero, hence the rotor slip is almost zero, hence the rotor also will almost be zero. Rotor frequency also will be almost zero. Okay, that is what we know. So there will not be any skin effect. At DC there is no skin effect, so skin effect is not there. So automatically the resistance will be reduced. Whatever I have to do, I just have to do it at starting. Okay, I have to make the skin effect starting. So what we'll do, in deep bar we will use bars that will have larger cross section area, so that the skin effect will force the current throughout the outer portion. We will see how we do that. And we have this deep cage rotors where we'll have two cages. One will be outer cage, inner cage. Outer cage will be higher resistance. Most of the current will flow through the outer cage because most of the current flows through the skin, right? Skin effect. So during starting, high resistance, most of the current will flow through that. So there will be high resistance. So I will get good starting torque, and the starting current will reduce. And during operation, full load operation, the inner part will provide low resistance. So overall resistance will reduce. During running, what will happen? The inner part will dominate because it will have lower resistance, because the slip frequency will be lower. Basically, what do I mean is, I told you, right, I have drawn this equivalent circuit, this one. So this is what we want to mimic basically. So basically what will happen, I will have a inner resistance and I will have a outer resistance. Okay, now sorry, this is, I wrote it opposite. I will have a outer resistance and inner resistance. Okay, now if the inner resistance is very low, okay, and the outer resistance is very high, but what do we know? We know the reactance is very low, right? Outer reactance is very low due to skin effect. So at high frequency, this reactance will be very high and this reactance will be low. So the ratio of reactance will dominate, basically decide current. Most of the current will flow through where? So at high frequency, both of these reactance will be very high compared to the resistance. At high frequency, both the reactance will be very high. So I will draw the circuit. So there will be two circuits. Okay, one will be low frequency, one will be high frequency. Okay, so here I will have high frequency. High frequency, like reactance is proportional to frequency. If frequency increases, reactance will increase. So this is high frequency and this is low frequency. So what I can say is that the circuit will be equivalent to this. Okay, and here the circuit will be equivalent to this. Why? It will be outer resistance and inner resistance. Why? Because of course frequency is 0, so it is simply short circuit, right? So only resistance are there. Low frequency, high frequency, this will dominate. So due to skin effect, this is higher and this is lower. This we know. Sorry, due to skin effect, this will be higher. Internal reactance will be higher than the external reactance due to the flux linkage. Already have been discussed. So at high frequency, basically during starting, most of the current will flow through the outer cage. Hence the reactance, hence the resistance here is higher. So basically my air gap power will be higher, right, during starting. But during running condition, it will totally, because the slip has reduced, so now the ratio will be decided by the resistance. So most of the current will flow through this Ri. So basically my power will be 3I square Ri. Ri is low, so basically the losses will also be lower here. Okay, we don't want to have a higher loss, right? Okay, so I hope you have understood this point. So this is what we'll do. Basically this is what we'll do. We will have a higher starting torque and good running efficiency. Running means when it is operating at full load. This is the main purpose basically. So for this, there are two things that you do. Okay, this is the difference basically. Two things that you do. One is a deep bar rotor. So not that important theoretically. Just you have to understand conceptually what we did. So this is the circuit diagram conceptually. This is the important portion. Rest here, right? This is just theoretical part. So we have this squirrel cage, right? Cage. All this whatever we are discussing are with respect to squirrel cage only. So all this whatever we're discussing are with respect to squirrel cage, because already wound rotor has the feature, right? Wound rotor has the feature. We don't need to do anything. Okay. So for deep bar rotor, what I can say? So for like there are two types deep bar. So deep bar basically means these cages there, right? Like what do you say? Small rods, aluminum rods. These are all aluminum rods. Aluminum rods. So what we'll do, if I see from this side, if I'm watching from this side, I will see this rods will come here. Okay. So I will make this rods more deeper. If I somehow make this more deeper, what will happen? If I make this more deeper, this rods more deeper, the thing that will happen is the skin effect will be more dominant. Why the skin effect will be more dominant? Because here, right, during starting the frequency is higher, so it will produce here like less amount of flux, and most of the flux, right, will be produced in the outer bar. Okay, basically what we'll do, we'll have two conductors. This will be the top conductor and this will be the bottom conductor. Now as the stator is near here, so the flux has to link, right? Flux has to link. So most of the flux will be produced on the top side during starting, because there is more AC current, right? So most of the flux, right, will be at the top side. There will be very low amount of flux in the bottom side. So most of the flux will be at the top side. Okay. So most of the flux is at the top side. So flux is higher in the top side. That means the magnetizing current will be higher. Basically most of the current will be flowing through the top side. Reactance will be lower, right? In the top side there will be lower reactance, in the bottom side there will be higher reactance. So most of the current will flow from the top where the resistance of the bar is higher. Okay, we will intentionally make the resistance higher, but reactance is lower, hence most of the current will flow through the top side only, top strip. Okay, there will be two strips. This is the top strip and this is the bottom strip. Okay. So yeah, I hope you have understood this point. So that is what we're doing basically. This is a summary. This is a summary. That is what we're doing. That's it. And during normal operation, what will happen is as the frequency is lower, it does not depend on the flux, because flux produced by the conductors will be lower because frequency is lower. So most of the current will flow through here. It will depend on the DC resistance, and the DC resistance of the bottom strip will be lower. So most of the current will flow through the bottom strip, not through the top strip. Okay, that is a summary. That is what we have discussed. The same thing, most of the current will flow through the top strip at starting, as it is mentioned. During normal speed, the current will be distributed basically. Similar current will flow, so there will not be any copper loss or iron loss, right? Because there is some iron loss in here, right? Because if you remember, this air gap power was equals to the rotor copper loss plus the mechanical power, right? So it is depending on the copper loss as well. Although I want the more mechanical power, but also if the current increases, copper loss is also there. So we have to be very careful regarding that. Okay, so that's why during running we don't always want that constant copper loss. During starting only we want constant copper loss, because I want the starting torque to be higher. Okay, so same thing is written over here. As the motor speeds up, skin effect will be negligible. So we don't like the deep bar rotor, there will not be any skin effect. So most of the current will flow through the lower resistance, so there will be very less amount of copper loss. Okay, efficiency will be improved. So this is how deep bar rotors offer dynamic resistance profile, high resistance at starting and low resistance during normal running operation. Okay, so this is the summary basically. Now what about the double cage? Double cage also something similar happens. Okay, double cage means instead of having a single cage, now I will have two cages. I will have two cages. One will be called as the upper cage, other one will be called as the lower cage. So now I will have two cages. If I have two cages, what will happen? If I copy this thing, right, inside I will have two cages. So if I have cage 1, like this is the inside cage, that is known as the lower cage or the inner cage. okay, inner cage, and this will be called as the upper cage. Okay, so basically what I can say over here is that, again, due to skin effect, initially most of the current will flow through the outside, right? So again, the upper cage will be of high resistance, so most of the current will flow through the outside, because the stator will be here, right? Stator, if you see, if I show you the stator, basically stator is, okay, this is not the stator, stator is somewhat like this, right? Stator will be somewhere outside. Okay, so if this is the stator, basically I will have to use some different color. So this is the stator. So most of the flux that will be generated inside this, right, that will, like, in the upper cage, that will link the stator. So most of the current initially will flow through here due to AC, due to skin effect. So most of the current will flow through the upper cage initially. So resistance of upper R up will be higher than the R low. R up will be higher than R low, and the reactance of up will be lower than reactance of low, but at high frequency, again the reactance will dominate. Again, this same thing, right? Same circuit. So conceptually this is same. This will not change. Just structurally we are making some differences. Okay. So that is what we are doing basically. So that is what we do. So there are two resistances. Okay. This RL and X2L and X2U, R2U. So R2U is higher, R2 dash U is higher than R2L dash L, but at high frequency reactance will dominate. So current will be divided according to the reactance. So the lower reactance, most of the current will flow. So X2U will be lower than X2L due to what? Due to skin effect. Okay. So yeah, I hope you have understood this point. So this is the approximate circuit and this is the analysis. Okay. So yeah, so approximately what you can do, if you have to analyze like what, how numericals can come, is you will ignore this, right? Ignore this resistance. Generally this will be larger at full load. So I can directly draw my circuit as this. I can ignore the, like, approximate circuit will be, if I neglect the resistance, okay, stated resistance, I can neglect it. So basically I can neglect, because all this will be much larger anyways, like reactance during starting also will be much larger, and during full load this resistance will be much larger. So I can neglect the stator resistance and reactance. So this will be my approximate circuit. This is what I will use for numericals. For numericals you just need to draw this circuit and you need to understand this particular thing, which resistance is higher, which reactance is lower. Okay, reactance will dominate at high frequency. During starting, reactance will dominate because these impedances will be high, right? That's why in series higher impedance wins, in parallel lower impedance wins. Okay, and during normal operation resistance will dominate. Okay, so this is the case basically. So what will happen, so this will provide some torque speed characteristics, this will provide some torque speed characteristics. Ultimately my current, right, I2 dash is sum of these two. So basically the upper cage will provide higher starting torque, but at full load it will provide lower torque. Why? Because the resistance will be like at like if the slip has reduced, so current will flow lower, right? Lesser amount of current will flow through this, higher current will flow through this. So that's why if you see, for the lower cage, it will provide more torque at full load because more current is flowing through the lower cage at full load, and at starting it is providing less torque because less amount of current is flowing. So if I superimpose these graphs, I will get my torque speed graph. Okay, so these are the things that you need to understand. You can go through, read through this. I am not reading through this. Okay, so you can see the comparison. What is the comparison? So like in case of deep bar, we use a single deep bar. In case of a double cage, we use two cages. And all this, whatever we are discussing, again I am telling you, all this is with respect to a squirrel cage induction motor. Okay, so starting current, mainly it will flow through the top of the bar due to skin effect. Mainly it will go through the higher resistance outer cage, okay, during starting. Running path, it will be uniform because it is DC. Throughout the bar, it will be uniform. So the resistance will be lowered. And in case of a double cage, most of the current will flow through the lower resistance path because there are two resistance paths directly connected. So most of the current will flow through the lower resistance because in DC, because slip is very low, so in DC resistance will dominate. So resistance will decide where the maximum current flows. Okay, resistance will flow through the lower resistance path. Okay, running condition, starting resistance will be high. Here also it will be high. Running condition, the resistance will become low. Okay, so this is what we want. We want higher resistance at starting because I want good starting torque. I don't care about the losses at that point of time, but at running I care about efficiency. So the resistance should reduce. Okay, so yeah, so let's do a question on this, and with this we will wrap up today's lecture basically. Okay, like very simple questions mostly will come, and in the next lecture we will discuss about harmonics in induction machines and also about the braking of induction motors. Okay, so one question is given: the standstill impedance of outer cage in a double cage is this. Okay, this is a standstill. Standstill meaning when my slip is 1 because rotor is not moving. So this is a standstill reactance, right, of the outer cage. Okay, fine. Outer cage reactance is given. .4, and the inner cage reactance is 0.1 here, and J 1.5. Remember, all these are with respect to slip equals to 1. So this is 0.3 divided by S where S is 1. This is 0.1 divided by S where S is 1. Okay. Assume stator impedance to be negligible. Determine the ratio of the outer cage current to the inner cage current and the ratio of the outer cage torque to the inner cage torque at the standstill. Okay, they are asking me what will be the ratio of the outer cage current to the inner cage current. Okay, so basically they are asking me to neglect the stator resistance. So I am applying a voltage across these two resistors, right? I just have to measure the impedance. That's it. That will be it, right? So standstill, I am comparing standstill, so it will be very easy. So if I write standstill, right, what will be the current in the outer cage compared to the inner cage? So basically it will be voltage divided by the impedance of the outer cage divided by voltage divided by the impedance of the inner cage. So this will be equals to Zi upon Zo, magnitude of Zi upon magnitude of Zo. So what is magnitude of Zi? Magnitude of Zi will be this will be 0.1 whole square plus 1.5 whole square Zo is 0.3 whole square plus 0.4 whole square. So IU upon II will be equals to 0.1 whole square plus 1.5 whole square, the reactance will dominate basically. At starting, you see at standstill reactance is dominating, okay, and this is point 3 whole square plus 0.5, so this will be 0.25 actually. Just hold on. 0.3 whole square plus 0.4 whole square whole under root into 0.1 whole square plus 1.5 whole square whole under root. So this will be 3. Almost it will come out to be 3. Okay. So you are observing that, you see, right? Basically whatever we discussed that the reactance of the outer cage is this, right? Outer cage reactance will be lower compared to the inner cage reactance, and at high frequency both this will dominate basically. It will depend on which is higher reactance, depending on the reactance. Okay, it will not mostly depend on the resistance, it will mostly depend on the reactance at high frequency, that is at starting. So you see that the outer cage current is higher than the inner cage current, that is basically. So what is the power now? So here the power will be 3 IO square into R, right? Outer cage. So most of the current is flowing through the outer cage. So R is higher here. So that's why I will get more power. Yes, there will be copper losses. Yes, there will be copper losses, but this is only happening at starting. So at running condition, the reactances will reduce. If the reactance will reduce, then the most of the current will flow through the inner cage. So then the loss will be, then also there will be torque developed, right? The torque developed will be equals to 3 II whole square into 0.1. In this torque developed, there will be bit portion that will be lost in the winding resistance due to copper loss, right? So, but as the resistance itself is very low, so the copper loss also will be lower. So that is our main purpose. That is our main purpose. Okay. So now let's calculate the, what are they asking? Ratio of the outer cage current to the inner cage current and the ratio of the outer cage torque to the inner cage torque. So what is the, all these we are calculating at standstill basically when the slip is 1. So outer cage torque to inner cage torque, right? So what is torque proportional to? Torque is basically, what torque is 3 upon omega s into I2 square into R2 dash divided by s, right? This is what my torque is equals to, right? So roughly divide by the inner cage, right? So what is the outer cage? What is the torque produced by the outer cage to the inner cage? So due to the outer cage, what is the current? That is I2U, right? Or I2O, right? Due to this outer current, this will be the torque produced. This is R2O, the outer cage resistance, right? And due to the inner cage, like speed, all these things will be constant. What is the current? That is I2 inner cage into R2 inner cage dash divided by S. Okay. So this will be basically I2O divided by I2I. I can ignore the dash for now. Whole square into S slip will get cancelled. Slip is 1 basically. A starting slip is 1, standstill, right? So this will be R2O dash divided by R2I, right? So I know what is the ratio between IO and II, that is 3 whole square, and what is the ratio between R2O and R2I? So R2O is outer resistance is 0.3, R2I is 0.1, so it is 3 divided by 0.1. So it will be 27. So I will get like 27 times the torque. So the torque produced by the outer cage will be 27 times the inner cage. That's why you see the graph, the torque produced by the outer cage is very high compared to the inner cage during starting. Upper cage or outer cage, whatever you want to say, same thing only. Now let's repeat this experiment at full load. Okay, calculate the same ratio, outer to inner cage current and the outer to inner cage torque at slip equals to 5%, that is at generally at full load. So when slip is 5%, that is 0.05, what will be happening? So this is right, this is equals to what actually? This is supposed to be equals to, this value is supposed to be equals to R2 divided by S, where S was 1, standstill, right? Now if S is 0.05, this will become 0.3 divided by 0.05. Okay, what will be the reactance? So reactance will not change, right? Reactance will be constant only. Okay, because reactance here, we have drawn our circuit such a way equivalently that reactance becomes constant. That's why we did this modification during the starting of induction motor. Remember, we did some modification, we take some things in common, right, to make the reactance to be constant. Okay, so it is independent of the slip. That is our main purpose, to make it independent of the slip. So reactance will not change, reactance will be same only. Okay, so if reactance is same, this will be 0. Uh, 0. Sorry, this will not change, this will be j 0.4. You will see that the reactance does not make any difference because the resistance will be so high that you can neglect the reactance during normal operation. You will see that this will be 0.1 divided by 0.05, and this was basically how much value? J 1.5. Okay, okay. So now if I am again applying the voltage, same current ratio, if I want to find out what is this value, this value, right, it 20 times. So 20 times this, so 0.3 divided by 0.05, so this is 6. So this is so high, right, compared to this reactance. So I can neglect this. So now which will be dominating? The resistance. DC, remember DC resistance will be dominating. So that is what we are seeing. So 0.1 divided by 0.05, so this will be 2. Okay, so basically if I want to find out the current, outer current by inner current ratio, it will be V by outer impedance divided by V by inner impedance. So this will be Zi divided by Zo. So this will be basically if I want to directly write, this will be Zi is, this is the inner one, right? So 2 square plus 1.5 whole square divided by 6 square plus 0.4 whole square, whole under root. Okay, so this will be 2 square plus 1.5 whole square divided by 36 plus 0.4 whole square, so whole under root. This will be 0.4157. Okay, so if you see, now the ratio is considerable. Okay, now the ratio is considerable basically. So both the current, like similar amount of current is flowing, and in the outer, if I see outer, basically outer current will be somewhat lower than the inner current, right, because it is 0.4 times the inner current. So inner current is higher than the outer current, so basically less losses. Now I am not focusing on the torque anymore, there will be less copper losses. This is the desirable thing, because the lower resistance is on the inner side, not the outer side. Okay, for torque, again you can do the same thing for torque analysis, same thing, right? Torque outer by torque inner will be equals to slip is same, right? So basically what will happen, it will be outer current divided by inner current whole square into outer resistance R2 outer divided by R2 inner. Okay, so outer current divided by outer, this in inner current is 0.4157 whole square into R2O divided by R2I. So R2O divided by R2I is, R2O is 2, R2I is 6, right? Sorry, R2O is 6, R2I is 2, right? So it will be 6 upon 2. So if I into 3, so again you are seeing that my outer torque is a fraction of the inner torque. It is 0.5185 into the inner torque, right? It is a fraction of the inner torque. That basically means that at full load the outer torque will be lower. That is what we are observing in the graph. At full load, due to the upper cage, the torque is very low, and due to the lower cage, the torque is higher. Okay, so I hope you have understood the graph as well. I hope you have understood the skin effect. Okay, all this we have considered, taken the ratio, understood conceptually actually what happens. Okay, within 40 minutes I have explained it. Other educators will just explain you the theoretical part, they will not explain you the numericals. Okay, you will not understand actually what is happening, why we are doing the deep bar and the double cage rotor, why we are doing it. Okay, because in normal wound rotor we have the provision to add rotor resistance, but in slip ring we don't have the provision. So we want to actually get higher starting torque. To do that, we saw we can utilize the skin effect, okay, to make the skin effect more prominent at starting. So that is what we have done. Okay, so that's it basically for this lecture, and in the next lecture will be the last one, where we will be discussing about the braking of induction motor and harmonics in induction motor. Thank you, and I will see you in the next lecture. Until then, happy learning.